Okay, so let's get going here. We'll discuss tests shortly. Today we will continue in Chapter 5. I don't think that we'll get to Chapter 6. Project number 3, just so you can start thinking ahead, is actually already out there. We will spend some time talking about project number 3, most likely on Tuesday, so please be prepared to have that with you. Looking farther ahead, notice test number 2 there. I anticipate that probably will be moved back to sometime the week of November 13th, but it won't be any later than November 20th. We'll just see how fast we get through some of the material for where that test will fall. Okay, so are there any questions before we talk about test number 1? Okay, let's talk about test number 1. I know this is small, but this is what I can't make it any bigger. This is a distribution of the grades for the tests. You know, overall the grades were decent. I mean, we did have a median of 85%, so that was pretty good. There are, well, first of all, you know, if you're not satisfied with your grade, please remember though, this is only 25% of your overall grade, so there's still a lot of the course grade that's out there for you to get. Generally speaking, probably one core test is not going to cause you to do very poorly in this class. Let's talk about a few specific problems that on the tests that I noticed some students missing. So first of all, let's look at number 2B. So if you remember, this was actually came from the homework. So this problem should have looked familiar to you. It involved the diamond prices data set. And on 2B, what you were doing was basically running my examine.mod.simple function to evaluate the model and to find potential problems with the model relative to the data. And in part I just simply asked you, well, is a predictor variable correctly specified in the model? Let's take a look at the corresponding plot that you would examine. So the plot, let me get my pen out. So you look at this particular plot here. Now, most of you said, well, there's a pattern in the plot, so therefore, again, we have a problem with the predictor variable. But you have to be careful, and I mentioned this with the last project, you have to be careful what you mean by a pattern. If you are talking about the fact that the variability in these points on the right side is a lot bigger than on the left side, well, that's not what you're supposed to look at with this kind of a plot. Rather, what you needed to say was that notice that there appears maybe to be some kind of trend, maybe like a quadratic trend, or you could say, well, the residuals are positive for lower values of x, and they are negative for middle values, and kind of a mix for larger values. That's what we're looking for with this kind of plot to determine if there's a problem with how we are specifying x in the model. And so that's what I needed to see. Please make sure you understand why, you know, I'm saying that perhaps a quadratic transformation would be good for x here. If you remember how we related in a very similar problem, we related this particular plot to a plot with the power load data and how it made sense. Oh yeah, quadratic would probably work out fine. So it was number 2B. Number 2C, so you need to say, well, what could be done? And there's a variety of things that could be done. What a few students said was, take y to the 0.5 power. In other words, do the square root transformation. And say that's because with the Box-Cox method we had a lambda hat of 1/3. And 0.5 is more interpretable, or more used to working with that, than we are, let's say, with a 1/3 transformation. And probably the reason why you said that was because that was some of the logic that I was using with the project number 2. But there was one key aspect that you, if you did say do the square root transformation, there was one key aspect that you missed out on, which we had in project number 2, but we did not have for this test. And that is shown right here. Let's see if I can make this bigger. Oops. So if we look at the Box-Cox transformation plot, notice we have a very narrow band for possible values of lambda. And 0.5 would fall right about there. In fact, you could actually calculate the interval and see 0.5 is not in the interval. Well, if 0.5 is not in the interval, then you shouldn't think that will be a possible value of lambda. And thus, a square root transformation would not make sense for this problem if you're referencing the Box-Cox transformation here. Okay. And lastly, number 3b. Unfortunately, there was a number of students who said this. So this gets at, well, describe what sigma squared measures. And a few students were saying that sigma squared measures the distance from the green point to the red line. No, that's what epsilon is. What sigma squared measures in is the variability of these distances. Big difference there. Big difference. Okay. So those were just some of the commonly missed questions on the exam that I just wanted to at least briefly address. If you have a question on why I took off a particular number of points on a particular problem on the exam, please come talk to me individually about that after class. If, however, you have a question about how to do a particular problem, please feel free to ask at this time. Are there any questions? Okay. And that's it for test number 1. Okay, that takes us then to Chapter 5, Notes. So in Chapter 5, we're starting to look at how matrix algebra can help us with a regression analysis. And so we have a lot of the basics of what is matrix algebra first, because there are a few students in here who don't have a matrix algebra background. It's not a prereq. It's not necessarily a specific prereq for the course, but it sure does help, obviously, to have had matrix algebra before. And so we're just going through some of the basics of matrix algebra. So for some of you, this might be, unfortunately, very boring. So I'm sure all my other lectures are very exciting otherwise. Others of you, this will be new stuff. But for most of you, the R aspect will be new. So concentrate on that. And generally speaking, on tests, on projects, what you need to know is the R aspect of matrix algebra. Because we're not going to do matrix algebra calculations by hand. Yes, you need to know some of the basics. But generally speaking, I'm not going to ask you to multiply two, let's say, 10 by 10 matrices together on an exam. Okay? So, we were talking about matrix algebra, we were talking about multiplying matrices together last time. And let's look at how we can do that in R. So let's say I have two matrices A and B. And just as a review, how do I tell R I have matrices? One way is to use the matrix function, where in the data argument you put in the corresponding elements of your matrix. You say the number of rows you have, the number of columns, and how you want to fill up the matrix with the stuff that's in data. So if I execute this here for A and B, we see A was created by putting in those numbers that it's in the data argument, put them in the matrix by row. You notice how it's a 2 by 3 matrix. Here's what B looks like as well. Now to multiply A times B, we just simply use A, and rather than only an asterisk, we actually have to use a percent, asterisk, percent, and then put in B. This is just the syntax that you have to use in R. And here's our corresponding result. So for example, this 5 here comes about through taking 1 times 3 plus 2 times 1 plus 3 times 0, and you get 5. Okay? Notice how A is a 2 by 3 matrix, B is a 3 by 2. Remember, you need the number of columns for the first matrix that you're multiplying to be equal to the number of rows for the second matrix. Also, then the end result then will be the number of rows in the first matrix is the number of rows in this resulting matrix, and the number of columns in the second matrix then is the number of columns in your resulting matrix. So I have a 2 by 3 here, a 3 by 2, I get a 2 by 2 overall. And you can see why those rules hold for the rows and the columns corresponding to how you're actually doing the multiplication from each row to each column. Okay? Now, what you learn in your grade school days is that if I took 2 times 3, that's going to be equal to 3 times 2. It doesn't, it doesn't matter what order you go in, right? Well, with multiplying matrices, it does matter. And so, if I do B times A, now notice how I get a 3 by 3 matrix then as my result, which obviously is different from the previous 2 by 2 matrix. Now you might be wondering here, why can't you just simply specify an asterisk to mean multiplication? Here's why. An asterisk in R means actually something a little bit different when you're working with matrices. So if I were to do A asterisk A, let me just actually show you A again. A asterisk A, look what happens. So what did R do? It does element by element multiplication. So, in other words, it took 1 times 1, 2 times 2, and so on. So it does element by element multiplication. Notice the end result. If I start off with a 2 by 3 matrix times a 2 by 3 matrix, in terms of the asterisk, you get a 2 by 3 matrix. So be careful about that. Well, what about if we work with some vectors? Now remember, in R's terminology, a vector is not necessarily a matrix. So notice how when we have a matrix A, you see rows and columns defined. But here, if I have just a vector X, through using the C function, notice you don't have rows and columns. You just have simply this 1 here indicating, okay, here's the first element. Well, what would happen then if I took A times X? I get this. So what did R do? Well, in order to do matrix multiplication, remember, I need the number of columns of the first matrix equal to the number of rows in the second matrix. So what R does, in order for the multiplication to actually work, it changes this X into a 3 by 1 mathematical matrix or vector. That's how R actually does it. It transforms your vector in R's terminology to a form where the matrix algebra will work out. So just to make sure you understand this, if I take 1 times 1 2 times 2, 3 times 3. Add them all up, get 14. Okay. Well, what about this now? Suppose I took x times x. What does R do? Now, especially if you have a matrix algebra background here, this can get confusing. What R does is what's called, in a mathematical context, an inner product, where the end result is one number. It transforms this to be a 1 by 3 and this to be a 3 by 1.
So basically that's dot.
Yeah. Now, you might be thinking, well, why didn't it do it the other way? You know, why didn't it think that this is, let's say, 3 by 1 and this 1 by 3? So the end result will be a 3 by 3. Well, it's just the definition of how R defines this percent, asterisk percent, in terms of multiplying matrices. If you actually wanted that 3 by 3 in the end, you can put an O instead of an asterisk there, and you get what's called an outer product. We're not going to use outer products in this class, but I just wanted to let you know that this happens. Okay. Are there any questions? Okay, page 13 then. So let's go back to the high school and college GPA data set and do some calculations like what we just did in terms of multiplying matrices. So if you remember with this particular data set, here's our X matrix. Notice how it has a leading column of 1s, and later today you'll see why that occurs. And we also have this vector Y. Yeah. Yeah.
If you want the vector that before, instead of using it as a vector, but just a number of scalars to multiply, we use just the answer. Basically, to produce instead of one matrix, say three matrices multiplied by a scalar.
I'm not for sure if I'm following you, but let me do this.
I mean, we have X is a vector, 3 numbers, right?
Yeah.
So if you want to produce basically each number by multiplied by the matrix.
You mean to do element by element?
What you did now.
Okay. Yeah. So that's what happens there, where A is this, and X is this. You just have to be careful when you do some of this stuff, because you need to make sure that you understand what the reaction is by R. And once you get used to it, then it becomes secondhand. Okay. Yeah.
What are the transpose and inverse operators on which?
Excuse me?
The transpose and inverse operators.
Yes.
In R.
Well, we actually did look at a transpose last time, and it's the T function, and we'll see it again actually in this example, and we will come across the inverse very shortly.
If you violate the rules of the multiplication, will it give out a warning, or will it transpose to?
If you have, let's say, 2 actual matrices, let's say A and B, and they are not the correct size, you will get an error message. Okay, so with this X here, if you remember, we actually have a sample size of 20. So this is actually, let me get a red pen. This is actually a 20 by 2 matrix. The Y is a 20 by 1 matrix, or you can say a 20 by 1 vector. And often, when we are doing stuff with regression models, we are going to be interested in these particular matrix, resulting matrices, where you take the transpose of X, or what I could call X prime, take that times X, so X prime X. I could take X prime Y and also Y prime Y. These are going to be very important coming up. Let's look at first how we can actually calculate these. So I can read in my data like I would normally. Let me actually go ahead and do that. And then to form the X matrix, where I had that leading column 1s, I used the C-bind function. C stands for column, so put the stuff in columns, bind them together. I'm going to combine 1 and also all my high school GPAs. Now notice there are 20 high school GPAs in the data set. Obviously there's only one number 1. What does R do? Well, R does what's called, in its terminology, recycle, where it makes sure that the stuff that's in this first part right here is the same size as the second part here. In other words, it will replicate that number 1 20 times. So that here is my X matrix. Okay, so it's just a convenience tool. Y is going to be the college GPAs, and let's do some matrix multiplication. So if I take the transpose of X multiplied by X, notice the transpose will be 2 by 20. X is 20 by 2, so the result is 2 by 2. The transpose of X is 2 by 20. Y is 20 by 1, so I get, in the end, a 2 by 1 vector. And then if I took the transpose of Y times Y itself, of course, I just get a 1 by 1. Let's look at some notes here. Well, let's look in general terms what this Y transpose Y, or transpose of Y times Y, actually represents. So if I take the transpose of Y, instead of having a row vector, I have a column vector. And so what that means is I take Y1 times Y1, Y2 times Y2, all the way down to Yn times Yn, and I add them up, and look what that means. Just simply, you're taking the sum of the Y squares. If I have X prime Y, then if I take my X matrix, remember these all are elements of 1. I just decided to write it out very general. Just elements of 1. And then if I take this row of 1s times this column of Y's and add them all up, look what you're left with, the sum of the Y's. In a similar manner, this row of X's times the column Y's, you get the sum of your, in other words, your sum of your predictor variable values times then their corresponding Y's. And lastly, I'll let you go through the details on your own here. This is what X prime X looks like. Notice how the 1, 1 element is simply n. Notice how you get sum of the x's. You get sum of the x's squared in terms of the predictor variable values. Well, why is that important? This is from chapter 1. Do you see some stuff over here that looks very similar to what we just calculated through matrix algebra? Yes, you do. You see sum of the x's times the y's. You see the sum of the x's. You see the sum of the y's. So you might be thinking, well, through all these matrix algebra calculations, maybe then I could calculate B1. And in fact, that's what we're going to do shortly. Another way to get the X matrix that's a little bit easier, often, if we were to actually use the LM function to estimate our model that results in mod.fit, there is a function R called model.matrix. You use that with mod.fit, you get your X matrix back. Okay, so some special types of matrices that will pop up now and then again. We can talk about a symmetric matrix. That just means that if you have a matrix A, you take the transpose of it, and let's say it's exactly the same as it was before, it's called a symmetric matrix. So for example, here's this matrix A, take the transpose of it, meaning, again, the rows become the columns. Obviously, you get exactly the same thing back. There are matrices called diagonal matrices. What that just basically means is that the elements that have the same row and column number could be non-zero. This is often referred to as the diagonal of the matrix, when your row number is equal to your column number. And everything that's off the diagonal is a 0. This is called, again, a diagonal matrix. Special case of a diagonal matrix is an identity matrix, where now all these diagonal elements are equal to 1. And sometimes you will see these, this little notation here, a J, little j, and a big J. This just means a vector of 1s or a matrix of 1s, simply put. Just notation. Section 5.5, linear dependence in rank of a matrix. This is going to be more important later on, but we're going to first talk about it here. Suppose we have this matrix A. And think of each column then inside the matrix as a column vector. Now note how I constructed this matrix. If I take 3 times the second column, I get the third column. When this happens, we say that the columns of A are linearly dependent, meaning one column is a function of another column or maybe multiple columns. This is called linear dependence, linear dependent. Oftentimes, we will be interested in the rank of the matrix, which basically just says, well, how many columns are linearly independent, meaning, columns are not functions of another one. And in this particular case, since we have this column 3 that's a function of column 2, we have a rank of what's called 2. Or, I guess I didn't say this, the rank of a matrix is the maximum number of linearly independent columns. The reason why this is going to be important, just to foreshadow some stuff later on, is that we're going to be very concerned about our X matrix. Does it have a rank that is equal to the number of columns? We need that to happen. So what this is going to mean for us is that we need to be very careful about what our predictor variable values are. We don't want one column to be a function of other columns. Section 5.6, the inverse of a matrix. So back in your grade school days, you learned about taking an inverse of a number. So if I have a number 3, and if I want the inverse of it, that's 3 to the negative 1, or 1/3. And if I were to take 3 times 1/3, what do I get always? 1. So in other words, if you take a number times its inverse, you get 1 back. Kind of like an identity. Well, we can do the same thing with matrices. So the inverse of a matrix A is simply denoted by A with a superscript -1. So if I take A times inverse of A, guess what I get? The identity. And in fact, if you took A times the inverse of A, if you took the inverse of A times A, you also will get the identity. So in order to flip-flop these positions here, for those matrices, what does A have to be in terms of the size? It has to be a square matrix, exactly. Because if it was not square, then you would have problems with the multiplications in terms of the rows and the columns matching up correctly. So, to give you an example of an inverse of a matrix, let's say we have this very simple matrix A. One could show, and I'll show you shortly, that here is A inverse. If you multiply the two matrices together, guess what you get? The identity matrix back. So how could you find an inverse of a matrix? Well, if you were to do this by hand, it can be kind of a long process. If you've taken a matrix algebra class, I'm sure all of you have done it by hand. If all of you have done it by hand, if you've taken that kind of a course. Here's just the simplest way that you can find a matrix. That you can find an inverse. This is for just a 2x2 matrix itself. So if I have this general matrix written out as A inverse then is the following. First of all, notice how I basically flip the positions of the elements that are on the diagonal. Also, the off-diagonal elements I put a negative sign in front of them. And then out in front, I take 1 divided by the product of the diagonal elements minus the product of the off-diagonal elements. There's your A inverse. I'm not going to ask you to do a calculation like this by hand, but this is how you get it. Now for 3 by 3 matrices, 4 by 4 matrices, it becomes a lot more complicated. You can't use that exact formula. But you can do it by hand. Taking a matrix algebra class is fun. But if we were to do it by R, how can we do this? Okay. Again, let's create that same A matrix that I had before. To do inverse in R, it's not like an INV function. It's actually the solve function that allows you to get the inverse. So if I were to take A then times solve A, look what I get. Practically the identity matrix. Of course, this right here is just about 0. Okay. Page 21, let's look at how this can be useful then in the context of the high school and college GPA problem. Here are 2 places where we will end up using the inverse. First of all, I want to take the inverse of x prime x, but also I want to take the inverse of x prime x and then multiply it by x prime y. This is what I get. Let me actually go over here to the word. Now previously, when we use the LM function to get our sample model, and we get our B0 and B1 out, this is what we had, and look what happens. If you're using that matrix algebra, we get exactly the same thing. So now you can start seeing how matrix algebra really is important here. It helps simplify the calculations. All you have to remember is x prime x inverse, x prime y gives you your B0 and your B1. Now the beautiful aspect of this little equation here is that we will start adding more predictor variables to our model. And for every predictor variable that we add to our model, we're going to have another column of our X matrix for that predictor variable. But in the end, we will still simply use this x prime x inverse, x prime y equation to find our B0, our B1, our B2, our B3, and so on. It will always be the same equation.
We would also hold when we add quadratic.
Yep. Yep. Now, if you had, let's say, a quadratic term, now you would, let's say, add another column that's for, let's say, x squared.
Basically treats it like an additional variable.
Yeah, exactly. So that's why, we go to a matrix algebra format basically for the rest of the course. Let's talk about this x prime x right here and why that's important. I'm going to deviate from the notes here. Let's see. So I guess in the notes, though, what I do is this. I take sum.fit gets the summary of mod.fit. Okay? And if you remember, to get my square root of MSE, I can take the sigma element out of sum.fit. And what I'm going to do is take that times then x prime x. Okay. So again, this square root of MSE is just one number, as what we saw before. If you take a one number, a scalar, times a matrix, all you do is take each element of the matrix times that scalar value. And notice how I can do that simply using the asterisk only. Now, if you remember, I had summary mod.fit here. Here's where I have the square root of the estimated variance of B1. Here's the estimated variance of B1 itself. Compare that to this little matrix that I had just found. Oh, what did I do wrong? Hold on. Yeah, I know what I did wrong. Sorry. I wanted MSE here times x prime x inverse. Compare this 2 element to when I had the estimated variance of B1. They are exactly the same. So now you can see how, using matrix algebra, how you can find that corresponding variance. And in fact, if I were to take the estimated, if I were to take the square of this 0.19941, you get 0.0397. Look at that. That corresponds to the 1,1 element of this matrix. We will talk about why that occurs a little bit later on. But again, I just wanted to show you why finding inverses, working with these X matrices is important. Are there any questions? Okay, page 523 then. Random vectors and matrices. So all of you know what a random variable is. Well, what about a random vector or random matrix? All that means is the elements of the vector or matrix are random variables. That's it. So we kind of saw this before, that our model, population model, can be written as y sub I is equal to expected value of y sub I plus epsilon sub I for I equal 1 to n. Well, we can put that more simply into a matrix where the elements of y are random variables. So this is a random vector. If I want to find then the expected value of a random vector or matrix, all I need to do is distribute the expected value into every single element. So for example, the expected value of y is just an expected value of y1, expected value of y2, down to expected value of yn. Expected value of epsilon follows a very similar form. Okay. So, page 24. It takes us to talk about something called a variance-covariance matrix of a random vector. Some people will just more simply call it a covariance matrix, and that's what I will call it. Who has not seen what a covariance is? Okay. Depending upon your background, you may or may not have seen what a covariance is before you get into this class. So I'm going to give you a brief description of what a covariance means. Let's consider the situation where I have 2 random variables, z1 and z2. Now, and I just changed this a little bit from the notes. I put a subscript I here to be more general. The variance of z sub I, of course, is the expected value of z sub I minus mu sub I squared. It's just the definition of what a variance is, where mu sub I is the expected value of z sub I. Well, let's talk about the covariance of z1 and z2. I can define this symbolically like this. Cov, parentheses, z1 comma z2. And it's this. The expected value of z1 minus mu1 times z2 minus mu2. So notice how this is very similar to a variance here. Practically what you're doing up here is you're taking z1 minus mu1 times z1 minus mu1. But now with a covariance, you allow for 2 different random variables to be in there instead. And what this is going to allow you to do is measure the relationship between the 2 variables. In other words, the dependence between them. If you have a covariance that is greater than 0, that means you have positive dependence. In other words, as z1 increases, z2 also tends to increase. So for example, with the high school and college GPA example, if high school GPA was, let's say, Z1, college GPA was Z2, you would expect a positive covariance in that kind of a situation. If instead, let's say your predictor variable, instead of high school GPA, suppose your predictor variable was number of arrests during high school. Well, if that's your Z1, then as Z1 increases, what would you expect for Z2 to happen? Generally speaking, Z2 would probably go down, and so you would have what's referred to as negative dependence. And in a covariance setting, that would be represented by having a covariance less than 0. When covariance is 0, that basically means that, well, you don't have dependence. You can say independence between the two random variables. So it's just a mathematical way that we can measure dependence between two random variables. Now, where I would anticipate that all of you have seen covariances though before, or seen this idea of dependence before, I should say, is through what's called a correlation. You may or may not have seen this formula before, though. If I look at the correlation between Z1 and Z2, I can define it this way. The covariance of Z1 and Z2 divided by the square root of the variance of Z1 times the square root of the variance of Z2. Well, and this also has the same property regarding dependence. Okay? Now, why do we have two things that measure basically the same thing? Well, one problem with the covariance is that there's not necessarily an upper bound or a lower bound. So, covariance could be 1, 2, 3, it could be 1,000, it could be 1 million, and so on. And so that can be make it difficult to interpret. The nice thing about this correlation here, and dividing by this part right here, it forces the correlation to be between -1 and +1. And so the closer you are to 1 or -1, the stronger the dependence you have. If you're at +1, that means you have perfect, a perfect relationship. If you're at if you're at +1 means a perfect positive relationship, meaning your high school GPA is a simple mathematical function. Your college GPA is a simple mathematical function of your high school GPA, for example. And you can think of it also in terms of if you have a -1, you have perfect negative dependence. Now, this then relates to something that all of you should have seen before coming into this class. I know I talked about in my Stat 801 course, and that's something called the Pearson correlation coefficient. The estimate of this correlation here is the Pearson correlation coefficient, without getting into the details of why it's the estimate. Okay. So you can actually calculate this on data. Some notes. If I were to look at the covariance of Z1 and Z1, that would mean take the expected value of Z1 minus mu1 times Z1 minus mu1 again. In other words, expected value of Z1 minus mu1 squared. In other words, your variance. Okay? So the covariance between the Z1 and Z1 is just the variance of that random variable. Okay. Now, where we are going to see covariances now and for the rest of the course is in what's called a covariance matrix. We're going to see lots and lots and lots of these. Let's define the matrix. Suppose, again, we have two random variables, Z1 and Z2. We put them into a vector. So we have a 2-by-1 vector. And then the covariance of Z is represented like this. The 1, 1 element is the covariance of Z1 and Z1. In other words, the variance. The 2, 2 element is the covariance of Z2 and Z2. In other words, the variance of Z2. Yes?
Why is the covariance, why is the expected value of the squared variance? I don't, the equation looks like you're just square.
You mean right up here?
Yeah.
Well, it goes back to what the definition of a covariance is. So let me get a highlighter up. So all I'm doing is applying this definition. So if I replace the one subscript here, I'm sorry, if I replace the 2 subscript with a 1, look what happens. You get basically the variance formula. Did I answer your question or not?
What's the equation, like the general equation for variance where do they expect it?
Right up here.
It's not like something like this.
Oh, I think you're expecting this.
Why isn't that?
It's the same thing. If you just multiply this out, you'll see that it all simplifies. It all comes down to this. Okay? So it's just 2 representations, exactly the same thing. And so also, you know what you might have seen in another setting too, I can actually write this covariance out. If I were to multiply out the elements inside the brackets, I can multiply this out and get expected value of Z1 times Z2 minus expected value of Z1 times expected value of Z2. So, you take a look at your 881, I'm sorry, 882, Casellenberger. Take a look at that. Okay. Notice the off-diagonal elements. So row 1, column 2, that's where you put the covariance of Z1 and Z2. But look at this here. Row 2, column 1 is a covariance of Z1 and Z2. So they're exactly the same as row 1, column 1. I'm sorry, row 1, column 2. Well, why? Well, it just comes down to, well, take a look at the formula. Does it matter which one that I put in there first? No, it doesn't. You're going to get exactly the same thing. So that's why, you could say, well, it's the covariance of Z2 and Z1, when in fact it's also the covariance of Z1 and Z2. It doesn't matter. You're getting exactly the same thing. So notice too then that this means that this covariance matrix is what? Has a special form. Symmetric. Covariance matrices are always symmetric. Please be careful when you are reading the book. The book uses a little bit different notation than I do. I use a different notation because my notation is by far a lot more prevalent than what the book does. So that's why I use it. So let's look at this in the context of a sample model. So the covariance of epsilon. So epsilon's a vector. There's epsilon 1, epsilon 2 down epsilon n in it. Now remember that epsilon sub I in our model are independent, mean of 0, variance of sigma squared. So my covariance matrix, which is n by n, should have on the diagonal corresponding variances, which are sigma squared. Now the off-diagonal elements will be like covariance of epsilon 1 and epsilon 2. But remember, they're independent. Covariance measures the amount of dependence, where at 0 means you're independent. So that's why you see these off-diagonal elements having values of 0. In fact, we could simplify this matrix form as just calling it sigma squared times I, the identity matrix, an n by n identity matrix. What's the covariance of Y? Well, let's think about what Y contains. It has epsilon, and has the expected value of Y. So you can think of beta 0 plus beta 1 times x. Is beta 0 a constant or random variable? Constant. Beta 1 is a constant. X is a constant. So the only random variable that could contribute to variances or covariances is epsilon. So as what was said, exactly the same thing. We'll have even a little bit more of a proof of that coming up. Okay. Some basic results of working with matrices that will be helpful to us that you do need to know. Let's say I have a matrix A. It has just simply constants in it. So just numbers. Not random variables, just plain old numbers. But we do have Y, which is a random vector. So it has random variables in it. And just to make things easy, suppose W is equal to A times Y. Then we have the following results that we're going to use again and again and again. Expected value of Y, expected value of A is A. Well, why? Well, it's like saying, what's the expected value of the number 3? Well, it's 3. It's a constant. What's the expected value of the number 1.5? It's 1.5. It's a constant. What's the expected value of W, though? Well, W has A and Y in it. This A is a constant, so what ends up happening is I can factor that outside the expected value. So that this simplifies down to A times expected value of Y. If you've had any kind of mathematical statistics course, this is why this occurs. So let's say I have a random variable Y1. And let's say Y1 has some distribution, we'll just call f of Y. If I want to find then the expected value of, let's say, 3 times Y1, and let's say that Y1 is a continuous random variable, then I would take the integral of 3 times Y1 times f of Y1 dy1. When you're working with integrals, of course, move that constant out. Okay, what about then the covariance matrix for W? Or in other words, the covariance matrix of A times Y. What ends up happening is that this A is factored out in 2 spots. This ends up being A times the covariance of Y, A prime. Okay? To relate this to something that some of you have had before, remember if you have a random variable Y1, you have a constant A. If you want to take the variance of A times Y1, what ends up happening is that this A is factored out and squared. This is, in terms of matrices, that's kind of the equivalent. You have an A and you have an A prime. Okay, let's take a look at some examples. Let's say here's my matrix A of constants, vector Y of random variables. So that means W, if I were to multiply things out, would be Y1 minus Y2 as the first element, and then Y1. Expected value of W, take this matrix and I move it out. And I get expected value of Y here, do the math, you see the result. And you can look at number 3 on your own, and you can see how working with these covariances ends up moving this A matrix out. Now, I understand if you haven't had a mathematical statistics course, some of these concepts, like what I was doing up here, are going to be a little bit difficult. First of all, I would tell you, take a mathematical statistics course. They're fun. You know, you need one of those if you're going to fully understand, you know, the statistical concepts of what we do and why we do it. If you have not had a statistical, if you have not taken a mathematical statistics course, then simply apply the results. Okay? I mean, we could spend a couple weeks talking about why this stuff is true, but we don't have a couple weeks to do it. This is an applied regression course. If you are not a stat major, a great course for you to take that's mathematical statistics based would be Stat 880. Okay, let's move on to page 29 now. Now we're going to get into the hardcore application of matrix algebra to what we're doing here with regression models. So again, here is our actual regression model. Notice how I have I indices on the y, the x, and the epsilon. And I ranges from 1 to n. So what this is basically saying, if I take a sample size of n, this is how our model is represented in terms of what we think of as the relationship in the population for these n elements of my sample. Since I go from I equal 1 to n, I could just simply write out the model like this instead, where I just iterate out from 1 to n all the different possibilities. This then allows you to see then how we put the corresponding elements into a matrix. So here's my y vector. Here is my epsilon vector. And notice here I have an x1, x2 down to xn, but I have no coefficients on the beta zeros. Well, you can think of, I actually do have a coefficient there. It's a 1. 1 times beta 0. So that's how we get then my X matrix. My betas, I could put those into a vector that has beta 0 and beta 1 in it, so that then if I write out my model now in terms of matrices, I get y is equal to x times beta plus epsilon. So notice when I take the first row of x, multiply it by my column vector beta, I get beta 0 plus x1 times beta 1. When I go to the second row of x times my column vector beta, I get beta 0 plus x2 times beta 1. So you can see how this 1, this leading column 1s, allows us to work with matrices in terms of our model. Are there any questions about that? Well, what about the expected value of y? Well, y is x beta plus epsilon. I can move the expectation through because it's just a sum. Expected value of epsilon, of course, is 0. So I'm left with just x times beta since those are constants. So the expected value of y is equal to x times beta in terms of matrices. This is the equivalent of what we were saying before. Expected value of y sub I is equal to beta 0 plus beta 1 times xi. Okay, page 530. Let's talk about how we find these estimates of beta 0 and beta 1. We've actually already kind of hit on this, but there's one main thing I want to mention. You will often hear people refer to things called normal equations when they are working with least squares estimation. These are simply the normal equations. It's just a system of equations that one can use to find what B0 and B1 are. These equations come about through using some calculus, through minimizing the sum of squared errors. I'm not going to ask you a question about normal equations ever on a test or a project. I just want to bring up this terminology because you may run into it someplace else. So if I solve for beta 0 and beta 1 here, I get my usual expressions for them. And in the end, in terms of matrices, you get x prime x inverse, x prime y. This is how we find our B. Where B has elements of B0 and B1 in it. I'll let you go through this on your own. I actually do the inverse. I actually do the multiplication all in terms of symbols. And you can see that we get exactly the same expressions for B0 and B1 as we did before. Okay, so high school and college GPA example. Actually, we've already done this example, so I'm going to skip this. It's a good place in the notes to mention it again, so that's why I did that. Section 511, this is page 534. Fitted values and residuals. Some people refer to our y-hats as fitted values. I've mentioned this before because we're basically fitting a line to the middle of those points on a scatter plot. So our fitted values are y-hat 1 to y-hat n, and we could actually put them into a vector, call it y-hat. Well, in terms of matrices, then, how do I find y-hat? It's x times b. Why? Well, again, put in your x matrix, put in your b vector, do the matrix multiplication, you can see how that comes about. Then that leads us to a particular matrix that's going to play a very important role for us. We'll use it some in the next few weeks, but it will be very important, especially in Chapter 10. This is what's called a hat matrix. Y hat is equal to x times b. Well, let's write out what b is. Again, x prime x inverse, x prime y. And just focus in on the x part. How about we call that H? That's what we define as the hat matrix. Does anyone know why it's called a hat matrix? Why is it called a hat matrix? So you take the matrix times y, you put the hat on top of y. Hat matrix. Okay. Again, this will be very, very useful more in Chapter 10. We'll still use it at times, but it'll be most useful in Chapter 10. Residuals. Well, we can define a vector E that has all of our residuals in it. In other words, it's just your y vector minus y hat. Well, remember what y hat is? H times y. So what we could do, we could factor out y. You get y times the quantity, the identity matrix, minus H. Okay? Where is that useful? Well, let's say that I want to find a covariance matrix now of the residuals. So the covariance of E. So like I showed you before, if I had covariance of A times Y, that's equal to A times the covariance of Y times A prime. Well, A in this case is I minus H. H contains X's. I obviously contains the numbers 1s and 0s. So this I minus H matrix is all a constant. So applying what we learn here, here's what my covariance matrix for E looks like. And if you remember what you told me before, the covariance matrix for Y itself is sigma squared I. So what I can do, let's write this as I minus H times sigma squared I times I minus H prime. Sigma squared is just a scalar value, so I can move this out in front. I is the identity matrix, so if I take I times something else, it's that something else. So that disappears. So I'm left with let me actually write it out. So I'm left with sigma squared times I minus H times I minus H prime. Okay. Then we have two other simplifications that occur. I urge you to actually look at an I minus H matrix yourself for any example that we do in class or some other data set. And you will notice two qualities about this matrix that always hold. First of all, I minus H is always going to be symmetric. And I minus h times I minus h is equal to I minus h. That nice little property corresponds to when you have what's called an idempotent matrix. Again, if you have a matrix out, if you've had a matrix algebra class, you've probably heard of idempotency before. If you haven't, don't worry about it. Just understand that if you have an idempotent matrix and you take them, multiply them by each other, you get the matrix back. Okay? So in the end, what's your covariance matrix? I minus h with a sigma squared out in front. That's it. What's your estimated covariance matrix, though? So, of course, remember, sigma squared is unknown. Well, let's replace it with its corresponding estimated value, mean square error. Notice how I put a hat on top of covariance there, because now it's an estimated value. Page 536. All this analysis of variance stuff, SSTO, SSR, SSE, can all be transformed into a matrix algebra format. I will let you look at the details on your own. And that takes us to page 540. The covariance matrix of B. Well, why do you have a covariance matrix of B? Of course, B0 and B1 are statistics. Statistics are random variables. Well, random variables have variances. They have covariances. The covariance of B, if I ask you to write it out in terms of the corresponding elements of the matrix, this is what you get. And one can show that it's equal to sigma squared times x prime x inverse. Have we seen that somewhere kind of before, earlier today? All of you should be saying, oh yeah, I remember that from about a half hour ago. Well, why is the matrix this? Well, let's go through a little proof. So the covariance of B, well, in other words, the covariance of x prime x inverse x prime y. Again, x's are constants. I can factor those out of that covariance. So I get x prime x inverse x prime times the covariance of x and x prime x inverse x prime, and then that thing has to be transposed. What ends up happening, and you can try an X matrix on your own, that this x prime x inverse x prime is actually a symmetric matrix. Covariance of y is sigma squared I. So factor out the sigma squared, the I disappears. Look what you're left with. X prime x inverse, x prime x. That's going to be another I, an x prime x inverse. And there's your proof. What's the estimated covariance matrix of B? Well, just put hats on top of everything. And replace the sigma square with MSE. There you go. This is actually what we had calculated earlier in the notes when we were talking about first x prime x inverse. Let's actually look at that a little bit more closely. So, with the high school and college GPA data set, I showed you earlier, MSE times x prime x inverse. Here are the here's variance of B1, variance of B0. Then what's this right here? The covariance of B0 and B1. All estimated covariance, estimated variances. So you can see that's what this covariance matrix was representing. Okay, estimated variance then in a confidence interval equation for expected value of y. If you remember, this is the expression that we had seen before. for that variance, the estimated variance that we use in our confidence interval equation. This can all be transferred now to a matrix algebra setting. Ends up being MSE times, create a vector x that has a leading 1 in it, and also your actual value that you're predicting at. So like with the high school GPA, this could be, let's say, x equals 3.0. If you're interested in confidence interval for expected value y at high school GPA at 3.0. You put in your x prime x inverse, and you put in your x again. Well, why is that? Well, it comes down to, again, some applications that we saw before. The variance of y hat will be the variance of now this vector x prime times b. I can factor out this x because it's a constant. Covariance of b, I already found before, and that's how you get it. You can do the same thing with the estimated variance with the prediction interval as well. Okay. We'll end with this then. Here's the high school and college GPA data set. I'm going to find my estimated covariance matrix for, I have cov.beta.hat. What I'm talking about is the estimated covariance of B. We've already done that. Now, let's see here. Another very important way that you need to know how to find this estimated covariance matrix, actually the easiest way, is use the function vcov. If I say vcov, and I've already fitted my model, put the model fit stuff from in mod.fit, you get the estimated covariance matrix out. Then what you could do is then use the corresponding formulas that we have just seen. So let's say I want to find a confidence interval when x is equal to 1.88. So I create my x.h vector, and then I have MSE here, my x.h multiplied by x prime x inverse, x.h again. Note that I can be a little bit sloppy in terms of using transposes because R will put everything into its correct form so that you can actually do the matrix algebra. So here's the estimated variance then for y hat. Let's see. And that pretty much then, you can find the interval like you would normally. Okay, that finishes chapter 5. Obviously, I went fast through some of this stuff because the aspects of what we're doing in regression analysis is nothing new. It's just how to transform the stuff into matrix algebra. You need to know the R aspects of how to do that. You know how to multiply matrices together? It's easy. You know how to use the solve function to get the inverse? It's easy. That's why I went through this stuff fast. Then once we get into chapter 6, we can then look at more statistical issues rather than mathematical issues like what we've been doing right now. Are there any questions? Okay, that's it for today.